Hello everyone, welcome to lecture 42 in the course Diffusion in Solids. So far we have discussed several aspects of diffusion. In fact, last week we also talked about the techniques to measure diffusivities, but primarily we have confined ourselves in the picture that the diffusion is happening in the lattice. And we have not really considered any other possible diffusion path. Okay. But you know that in a material it is not just the lattice, but there are other possible channels for the diffusion to take place. One of the very important is the grain boundaries. Okay. So, today and in the upcoming lecture, we will try and talk about the grain boundary diffusion. So, today we will look at the description of the Fisher model, which is used to understand the grain boundary diffusion, and write down the approximate and the exact solutions for it. We will not go into very detailed derivations. I will make it clear as we progress. So, as I said that other than the lattice, there are other diffusion paths in the crystalline solids. So, these are schematically shown here. You have the grain boundaries, dislocations and the free surface other than lattice where the diffusion can take place. So, you will have diffusion can occur through free surface, the grain boundaries and dislocations. And depending upon the temperature and other conditions, sometimes the contribution of these paths can be significant, that you have to take them into account. Grain boundary for example, contributes a lot at the lower temperatures and so on. And usually, if you in general plot the hierarchy of the diffusion coefficients, then the lattice diffusion is the slowest, followed by dislocation movement, then higher is the grain boundary diffusion, and the highest is the surface diffusion. Because you can imagine that in the lattice the atoms are have a more periodic arrangement, whereas in the case of grain boundary, let us say the atomic arrangement becomes distorted. So, there is more open space for the atoms to move. Now, why actually we should just to tell that it is quite intuitive that if the diffusivity follows this trend, the activation enthalpy will follow the reverse trend. That means, it will be highest for the lattice, followed by dislocation, then grain boundaries, and then the free surface. Now, why we should study the grain boundary diffusion at all? Okay. So, very simple answer is that grain boundary exists. Okay. So, grain boundary diffusion is studied for 2 or 3 important reasons. First is that how much influence it has on the lattice diffusion itself. If you remember when we were talking about the radio tracer technique, then in that we also note down some points, what are the deviations in the Gaussian profile that can occur, and one of the reason was the grain boundary diffusion. So, that means, if you do not take grain boundary diffusion into account, the estimate of lattice diffusion itself can be erroneous. So, one reason for studying grain boundary diffusion is to understand its effect on the lattice diffusion itself. Second is the grain boundary diffusion kinetics sometimes can give us insights into the nature of the grain boundaries and the structure of the grain boundaries. So, for example, the grain boundary diffusion can indicate whether it is if it is a very slow diffusivities in grain boundary or very high diffusivities in grain boundaries, then they hint towards equilibrium and non-equilibrium grain boundaries. Or sometimes it can also indicate low angle grain boundaries, high angle grain boundaries, because there the diffusivities are different depending on their nature and so on. And third, very important reason for studying grain boundary diffusion is there are several phenomena in materials which are controlled by grain boundary diffusion. Some of them are listed here: discontinuous precipitation, diffusion induced grain boundary migration, recrystallization, sintering, Coble creep for example, and these are particularly important below 0.6 Tm. So, and when you want to develop, let us say, models for the kinetics of these processes, you need the grain boundary diffusion coefficients as the important inputs. So, for all these reasons, it is very important to understand the grain boundary diffusion. It is fairly complex, though. The mathematical treatment, I will explain you why, what is the major complexity that it comes. Just one more point, importance of studying grain boundary diffusion is when it comes to thin films. Now, you know that you have so much electronic devices where a lot of material is used as thin films. Now, in the thin films, there are a lot more fraction of grain boundary than you have in your bulk materials, and then the grain boundaries are also sometimes oriented in certain directions and so on. So, if the diffusivities along these grain boundaries are high enough, then the presence of this grain boundary can lead to formation of detrimental phases or growth of these thin films sometimes to the undesirable extent, and which can influence the integrity and stability of the thin films, and ultimately it will affect the performance of your device. Now, how do we study the grain boundary diffusivities? As I said that it is not very straight forward, although now there are models developed, but still we will see that it is more difficult than to measure self diffusion. So, people try to basically give out some empirical estimates. These are two references by Brown and by Gust, who try to give some empirical relation for D0 and delta H GB for FCC, BCC and HCP structures. So, where the correlation with the melting point was tried to be arrived at. So, for example, in this you can see that it is 83 multiplied by Tm. Here the factors are different for BCC and HCP. From the reference 2, it is these factors are slightly lower, and similarly D0 is also predicted. So, this is basically to enable at least some estimates of the grain boundary diffusivities where experiments are difficult to perform. So, before we go to the diffusion behavior of grain boundaries, just quickly I will, we already saw this in the week where we discussed the atomic structures or the crystalline structure and defects. We saw that there are several types of grain boundaries, for example, tilt boundary, twist boundaries, and therefore, and there can be twin boundaries. So, depending on the grain boundaries types and structure and energy, the diffusion can also be different. Then grain boundary diffusion is different. I already told you if these are high angle grain boundaries or low angle grain boundaries, because that determines the energy of the grain boundaries. So, you have to understand that ultimately the rate at which an atom can diffuse inside a grain boundary or a lattice or any medium, so to say, it depends upon the atomic structure of that particular medium. So, if it is a grain boundary, the structure largely determines how much are the open spaces available, what is the energy of this grain boundary, and which will also decide, which will also play a role, how fast or how slow the atomic movement is through them. So, now moving ahead, how do we understand the grain boundary diffusion? See, one thing that happens is when we were considering the lattice diffusion, typically you saw that we considered one dimensional diffusion, and that was good enough for us to arrive at several analytical solutions, and we know by the symmetry that this can be extended to other dimensions as well. Even in non-isotropic materials, you can have certain linear combinations and work out. But when it comes to the grain boundary, we know that in the case of grain boundary, it is a 2D defect, and also the thing is that the diffusion can happen it is not easy to describe the diffusion through grain boundaries only in one dimension, and the reason I will explain you shortly. So, the very simple model, first of all, grain boundary is not a just a straight slab. It is you already saw in the previous that it can have different angles. It need not have a straight line. It need not be present as straight line. It can be curved and so on. So, how do you understand diffusion in such a complex path? So, the simplest model that was proposed was by Fisher, where what he said is that let us assume the grain boundary as a rectangular isotropic slab of high diffusivity embedded in a low diffusivity isotropic crystal. So, this means you are considering this grain boundary slab here, and it is a semi-infinite. So, it is not curved, it is uniform. So, the structure does not change along this slab, and it is isotropic, and it is embedded in a low diffusivity isotropic crystal. So, on both the sides you have grain 1 and grain 2. Now, grain boundary is described by two physical parameters. One is the width of the grain boundary, which is delta, and grain boundary diffusivity, which is dGB. So, during the tracer diffusion annealing, suppose if you deposit the tracer on the surface here, then the atom can diffuse in this specimen in two ways. One, they can diffuse directly into the grain, or they can diffuse much faster along the grain boundaries. Now, the twist comes here. The atoms which go to the grain boundary, they will eventually leave it and continue their path in the grains, okay, giving rise to a lattice diffusion zone around the grain boundary. Remember, the moment they are coming here, there is also a flux, there is also a concentration gradient which is in this direction, in the y direction. Okay. So, therefore, they will eventually come out of the grain boundary and move into the grain. What that means is that it is not just sufficient to consider diffusion in z direction, but you also have to consider diffusion in y direction. This itself makes our life a little complicated, because so far we could consider one dimensional diffusion, now we have to consider two dimensional diffusion. The second complexity that comes is that so far whenever we considered concentration profile, we had one concentration function C of x comma t. Here, now you have concentration within grain and you have concentration within grain boundary, and since the diffusivities are different along the grains and along the grain boundaries, so you have to use two different functions to understand the overall behavior. So, one is the concentration within the grain, which is coming by direct diffusion, that means direct the source is diffusing, plus the leakage from the grain boundary. So, that means whatever has come here, it tries to move out into the grain. So, that also contributes to the grain concentration. So, the C represents the concentration within grain, which comes by direct diffusion plus leakage from grain boundary. Whereas, another concentration function CGB is equal to concentration within the grain boundary. So, now if you try to apply the Fick's second law in two dimensional domain, then you can write dou C by dou T, here C represents the concentration within the grains, is equal to d dou square C by dou y square plus dou square C by dou z square for y greater than equal to delta by 2. Remember that origin is at the center of the grain boundary. So, anything greater than delta by 2 actually falls into the grain. Similarly, you can write dou CGB by dou T is equal to dGB times dou square CGB by dou y square plus dou square CGB by dou z square. Now, what are the boundary conditions here? For the self diffusion at the interface, there should be a continuity between the concentrations and the fluxes. So, C at plus minus delta by 2 comma z comma t is equal to CGB plus minus delta by 2 z comma t. So, this is the continuity of the concentration. Similarly, the flux also, there is a flux which is coming from grain boundary to this grain. So, if you calculate the flux using the grain boundary function value, that is different, that should be same when you calculate using the grains also. So, at y equal to delta by 2, the value of flux should be equal. Okay. Now, this j can be written as minus d dou c by dou y at y equal to delta by 2 is equal to dgb by, into dou cgb by dou y at y equal to delta by 2. Using these and also using the fact that delta is very small and dgb is much greater than d, these equations have been simplified as follows. So, the first equations remain same. The second equation dou CGB by dou t is equal to dGB into dou square CGB by dou z square plus 2d by delta into dou c by dou y at y equal to delta by 2. So, the first term you can see that it is like your Fick's second law, it represents direct diffusion into grain boundary, whereas the second term is the what is known as leakage flux. Now, the question is, how do you still solve it? You have this equation, how do we solve it? So, to solve it, because you see that you have the variables here which are z, y as well as time. So, what was done is to solve is to introduce the normalized variable. These normalized variables are psi equal to y minus delta by 2 divided by root dt, eta is equal to z by root dt, beta is equal to delta minus 1 into this delta divided by 2 root dt, where this del is equal to dgb by d. This is approximated as delta into dgb by 2d into root dt. Now, these parameters are just are dimensionless, which was essentially used to simplify the analysis of the diffusion equation, but they also have a certain physical meaning. For example, psi x represents the extent of lateral lattice diffusion from grain boundary into the grains. So, this is y minus delta by 2. Eta, it represents the influence of direct diffusion. So, that is why you see that you have z by root dt, and beta, which is also known as Leclerc parameter, it is a measure of extent to which grain boundary diffusion is enhanced to the lattice diffusion. So, delta into dgb by d into root dt, this ratio is a sort of measure of extent to which the grain boundary diffusion is enhanced in comparison to the lattice diffusion. So, the solution in terms of dimensionless variables, now C is written in terms of psi, eta and beta is equal to C1 times eta plus C2 times psi eta beta. This is within the grains. So, within the grains also you see there are two components, eta is only dependent on z, whereas the second component is dependent on all the three factors, and then within the grain boundary C of eta is equal to CGB of eta. So, now, so remember these are still the generalized cases. Depending on the geometry of the problem or other conditions of the problem, the solutions are written. So, for example, you have the constant source solution. So, we saw this constant source condition when we were talking about diffusion equation. So, in this case the initial and boundary conditions will be at t equal to 0, the concentration is 0 for any z greater than 0. That means, there is a surface concentration, but below that there is no tracer atom. At z equal to 0 and at any instant t, always the surface concentration is maintained as C naught. At z equal to infinity and any instant t, the concentration is 0 because we assume it as an infinite domain problem. The diffusion depths are much smaller than the overall dimensions of the sample. Here C naught represents the surface concentration which is maintained throughout the experiment. Now, quite often because you see that in fact that Fisher model picture also tells you that the concentration which is within the grain boundary is much less than the concentration which is outside, and the depth to which if the diffusion happens through the lattice. So, if the root dt is much greater than the grain boundary width, then quite often the CGB contribution is neglected. So, the approximate solution is given as C1, the part C1 is given as C naught into error function eta by 2, which is C naught complementary error function of eta by 2, which is equal to C naught into 1 minus error function of eta by 2. This represents the diffusion into grains. This should also tell you that this is looks similar to the carburization solution that we arrived at. So, some similarity is there, not exactly, but it is dependent on the error function or the diffusion couple where we saw that which is given by the error function approximation. The second part is more complex, and I have just given the equation. I do not expect that you memorize this equation. The derivation of this is quite tedious, and this is given by this rather complicated expression where sigma is an integral variable, but it depends upon all the three eta, psi and beta. Similarly, for the instantaneous source, now the boundary conditions will change. At t is equal to 0, the concentration at the surface is m. At t equal to 0, for any z greater than 0, the concentration is 0. At z equal to infinity, the concentration goes to 0. Again, it indicates it is a infinite domain problem, and the dou c by dou z at z equal to 0 is also 0. So, in this case, the exact solution again CGB term was neglected, and C1 that is the direct diffusion part is written as m by root pi dt exponential minus eta square by 4. This should also ring some bells of similarity to the Gaussian solution that we arrived for the instantaneous source. It represents the lattice in diffusion, the direct diffusion into grains. The second part, again you have the 2 dimensions involved here. So, it is rather complex, and it is represented by this integral. The exact derivation of this is beyond the scope of this course, but I am just giving you the expression to impress upon you the complexity of analyzing the grain boundary diffusion problem. And further for this instantaneous source case, it can be shown that integral 0 to infinity of C2 basically is equal to 0, which essentially means that the mass actually is conserved, and whatever you had was from 1. Quite often when you are doing the tracer experiment, it is also important to have some kind of estimates for the average concentration. So, for example, you want to know in this layer of thickness delta z, what is the average concentration of the tracer, not the separate C and CGB, but what is the average concentration in the thin layer at some distance z. So, average concentration is estimated let us say in a thin section between z minus delta z by 2 and z plus delta z by 2 and parallel to the surface, and it is given by this triple integral which is 1 by Lx into L into delta z, and these are the integration limits for each of the dimension, and here the integration is done for the both the terms C of y z t plus CGB of y z t dx dy dz, where Lx is and L are dimensions of this is like a bicrystal of the bicrystal along x and y axis, whereas this term, this represents the volume of this section. Now, to simplify, what is assumed is that this lies in the center of the bicrystal, and the section is so thin that along the z axis the variation is not much. So, that means you can remove that integral. So, therefore, ultimately it comes to C bar is equal to 1 over L minus L by 2 to plus L by 2 C of y z t plus CGB y z t into dy, because dz you are basically saying that there is no variation. And again for the simplicity, we also assume that it lies in the center. Now, C is a even function, and CGB is nearly constant within the grain boundary. So, therefore, further this equation is simplified to written as delta by L CGB bar z comma t plus 2 by L integral delta by 2 to L by 2 C of y z t dy. You can write this expression in terms of the dimensionless variables also, but if before that, if CGB is small, then you can neglect that term, and you can write C bar as 2 by L C of y z t, which again can be written as C1 which is only direct diffusion, plus C2 which also takes care of about the diffusion from the y direction. So, again, since C1 is constant in xy plane, you can write C bar as C1 z comma t plus 2 by L integral C2 from delta by 2 to L by 2. And you can convert this into the dimensionless variables. So, where C bar eta comma beta is written as C1 eta comma t plus 2 root dt by L into this integral. And a further simplification of this is C bar is C1 plus 2 lambda root dt from 0 to k C2 into d psi here, and where k is L by 2 root dt and lambda is equal to 1 by L for the bicrystal. For uniform spacing, if it is not a bicrystal, then you can substitute it with the ds. And for the polycrystals with the grain size d, this can be written as d by 2 root dt. Just one thing before we end today's lecture. So, we saw this equation or the boundary condition rather, where the concentration at the interface from the grain and from the grain boundary we equalized. That is valid if there is no, that is valid only for self diffusion. If there are, we consider solute diffusion, if there are solutes, then there is a possibility of the segregation of these foreign atoms. And the segregation means that excess concentration of foreign element can be there in the grain boundary. So, in that case, the boundary condition is modified as S into C delta by 2 plus minus delta by 2 z comma t is equal to CGB plus minus delta by 2 z comma t. So, this S is known as the segregation factor. And for this boundary condition also to be valid, it is important that, or it is assumed rather, that the segregation is in local equilibrium. That means there are no changes as you change the time. So, the segregation is has achieved the local equilibrium at any given depth, and also S is only a function of temperature and not a function of C itself. So, that along the boundary S is not changing as the concentration is changing, or concentration in the grain is changing. So, this is we will talk a little more about the segregation factor in the next lecture also, but when you talk about the solute diffusion, segregation is quite often important to take. So, with this we will end today's lecture, and we will continue with grain boundary diffusion in the next video. Thank you.